Today, we are diving headfirst into the absolutely wild world of quantum physics. And for this explainer, we're digging into a fantastic conversation with theoretical physicist Dr. Doris Ryder on the Under the Microscope podcast. She's working on tech that seriously feels like it's straight out of science fiction. But believe me, its impact on our future is incredibly real.
This quote from Dr. Ryder really says it all, doesn't it? Just try to imagine a world where the normal rules of how things are supposed to work, they just don't apply anymore. That's the quantum realm for you. It's the universe at the tiniest scale. And well, that's exactly where our story kicks off.
So yeah, our guide on this journey is Dr. Doris Ryder. She's a theoretical physicist over at TU Dortmund University, and her work is right on the cutting edge of quantum theory. She's figuring out how to use this strange science to build practical solutions for some of our biggest digital headaches.
Okay, so first things first. Let's talk about why we even need something called quantum mechanics. It really all boils down to the fact that the universe seems to be playing by two totally different rulebooks.
You know, in the world we all live in, things are pretty predictable. You drop a ball, it falls. That's classical physics, stuff we can see and touch. But as Dr. Ryder explains, when you zoom way down to the nanoworld of single atoms and particles, those rules just completely fall apart. Down there, you need quantum mechanics, a set of laws that are frankly bizarre, based on pure probability, and are nothing like our everyday intuition.
So why should we care about all these weird, tiny rules? Well, here's the kicker. If we can learn to use them, we might be able to solve one of the single biggest problems of our digital age: how to create communication that is truly, fundamentally unhackable.
The whole idea behind quantum communication is just revolutionary. See, instead of sending data the normal way, you send it using single photons, literally the smallest possible packets of light. And the security feature is baked right into the laws of physics. The very act of an eavesdropper trying to look at one of these photons, it disturbs it. It changes it. That means you would know right away that someone was listening in. Your security isn't just a password. It's guaranteed by the laws of nature itself.
So what's the secret sauce that makes this all possible? It's a core principle with a pretty great name: the no-cloning theorem. Think about it. A hacker wants to copy your data, read it, and then pass the original along like nothing happened. But this theorem says that's impossible. You literally cannot make a perfect copy of an unknown quantum particle. The moment you measure it to see what it is, you change it forever. You can't copy the key without breaking it.
This all sounds amazing, right? Unhackable communication, but there was a huge technical problem standing in the way. To make any of this work, you need one very specific thing. You need a totally reliable source of single photons. Not a stream of light, not a random burst, but one. Precisely one photon, on demand, every single time. So the question becomes, how on earth do you build a machine that can do that? Dr. Ryder has this brilliant way of explaining the old method. Just picture a quantum emitter, say an atom, as a person standing next to a high dive. To get it to release one photon, you have to give it a burst of energy, or excite it. It's like climbing a ladder to get to the top of the diving board. Once you're up there, you jump, and that splash in the water, that's your photon. The problem? That ladder has to be exactly the right height. It's really restrictive.
And this is where the story gets really good. This is the breakthrough. Dr. Ryder and her team came up with a new, super clever, and honestly just elegant way to get to the top of that diving board.
They started by asking a simple question: what if you don't have that one perfect ladder? What if every ladder you have is just a little bit too short to reach the top? It sounds like you're stuck, right?
Well, here's the ingenious solution. Instead of one perfect ladder, they figured out how to use two ladders that are both too short. By zapping the atom with two different pulses of energy in just the right way, you can swing up. It's like you use the momentum from one little jump to propel yourself up to the next level, and boom, you're at the top. It's a whole new way to get that atom excited and release that one perfect photon.
And of course, a method this cool needs an equally cool name. It's called SUPER. And yes, it's an acronym. It stands for Swing Up of Quantum Emitter Population. I mean, how perfect is that? a name for a method that lets you literally swing your way up to creating a single photon.
Now this was a fantastic idea cooked up by a bunch of theorists on a computer. But for me, the most exciting part of this whole story is what happened next.
And you can just feel the excitement in what Dr. Ryder says here. There's really no better feeling for a scientist than to come up with an idea that only exists in math and simulations, and then to see someone in a lab actually build it and it works. That yes moment, that's what drives all of science forward.
And the journey for super was unbelievably fast. Dr. Ryder's team came up with the theory, they published it, and almost right away, experimental labs all over the world were in a race to see if they could make it work in the real world. And the best part? It worked. It worked exactly like the theory said it would. It was this huge validation of their work.
So what's the bottom line here? What should you take away? 1. The quantum world is super weird, but its rules are incredibly powerful. 2. By using those rules, we really could build unhackable communication. 3. Clever thinking, like the super method, is how we solve these really tough problems. And 4. When theory and real-world experiments connect, science can move at lightning speed.
The super method is a massive step forward for all kinds of quantum technologies. But, it's really just one more step, and it leaves us with this huge, exciting question. As we get better and better at speaking the language of the quantum world, what other impossible things are we going to build next?